Yeah, Tyler had a question. Emailed me a question. He was doing a com, which does a one's complement.
Yeah.
And what were we doing? 0?
Oh, yeah, it was com 0.
Yeah, he did a com. It just does a complement. So he had com of 0, 0, right? And what happened was he received back. Did you use a register?
Yeah. I just
Well, whatever. His result was, I mean, obviously the result's going to give you FF, okay? Because I mean, you're just complementing all the zeros, going to give you all the ones. The carried flag was equal to 1, or no?
Yeah, the carrot was 1.
Carried was 1, and the sign flag was 1.
Right, and the end flag.
Yeah, and the end flag. All right. The reason that the carried flag was set equal to 1 was because in signed arithmetic, it looks at the what you're doing is a subtraction. All right, it takes a subtraction. We'll get to this when we get to chapter 5 on Friday. But it does a subtraction, and basically when he does a subtraction, his result came out to be negative because the obviously the most significant bit here, bit 7, is 1. All right, and it sets the carry flag for you. But we'll get to it. But the whole thing was, I think it came out due to the subtraction. That was the issue. Okay. All right. I wanted to go back and revisit because I had a couple emails or kind of a couple questions on this IO addressing and what's going on here. All right. Let me just get back to this thing. This IO addressing is going to be different for each processor. Okay. Now, there's a way to get around it where you don't even have to worry about it. Okay. But you'll notice here that there are 2 addresses here. Okay, there are 2 addresses. All right. This one here, and I'm just picking out of the 169 manual, the port B register. But this works for all ports. You'll see a 05, a 04, and a 03. And to the right of that, you'll see 25, 24, and 23. Anybody want to tell me what the difference between those 2 numbers is? Anyone want to take a guess or think about it? I mean, why do we have 2 addresses for, this is an 8-bit pin, all right? This is pin B. This is the input pin for port B. This is the data direction register for port B. This is the port B output, Mr. Lebowski.
One's the RAM address and the other one's the IO address?
Exactly. The numbers 05, 04, and 03 are what are called the IO address. The ones on the right are the SRAM addresses, all right? You can address these both ways, all right? I can use, if I use the in command, if I do an in, let's say in R17 PINB, all right? What that's going to do is grab the contents of pin B and pull them in to register R17. I could also do it this way. I could do an in R17 and give it the IO address, which would be 03. That is exactly the same thing. I could also do a let's see, ST store, I believe, into R17. Now, again, this is now, when you do an ST, what does the S stand for? We're talking SRAM here. All right, so now I don't give it the IO address. What do I give it? The SRAM address, which would be those 3 things do exactly the same thing, all right? Because again, everything is stored in SRAM, okay? So I have SRAM I have my 32 general purpose registers. Then I have all my I/O stuff. So this is SRAM, and that's going to go to SRAM. This stuff still goes to SRAM, but it's just using a different addressing scheme. Does that make sense? All right, let's pull up an example and let's do an example. And that's, if you go into the LSS file, you will see it equates pin B with the number 3. It equates the data direction register for B at 04, which is here. It equates port B with 05, which is, there's port B. Okay, so that's what it's doing. In the LSS file, it takes care of it for you. Typically, you don't have to use these two methods. You can just use pin B or DDRD or whatever instead of having to go and physically do these. But the only reason is I'm showing you that there are 3 ways you can address this stuff. Mr. Lebowski.
Does that third one work? Because the ST is talking about.
I need an STD or something. I got to do something here. Just hold on. I'll show you how to do this. I have an example coming up. Just take a second. But the idea here is, in the LSS file, it does all this for you. So if I'm going to address port C, the I/O address is 6, 7, and 8. If I'm going to address port D, it's 9, A, and B. Okay. Now these are all different depending upon what processor you're using. A 32 is different from a 169, which is different from a 2560. Okay. So usually, if you don't want to memorize this stuff, just use port B, pin B, whatever, DDRB, DDRD. Okay? It's an easier way to just remember what's going on. All right, so again, there's 3 ways to address this stuff. All right? I can do an in from 03 into R18. What that's going to do is grab the contents of port B and bring it into R18. Okay? I can do an out of R18 into the 08 I/O address. That I/O address happens to be port C. Okay? So it's just another way of doing it. All right? I can do an in pin B R18. All right? Same thing as this. Okay? I can out port C R18, which is basically the same thing as this. Okay? STS R18 into the number 25, which writes SRAM to port C. Okay? So it's going to take R18 and writes it to SRAM location 25, which is there. Okay, so try the STS. You'll be all right.
You just had it reversed.
Huh?
You had it reversed at the bottom. That's what was confusing me.
All right. I'm trying to confuse. Designed to confuse. And I think I added a new slide to your stuff. Yeah, here I'm showing you a bunch of different ways to do it. So why don't we run this code and then we can see. So let's bring up your Atmel Studio. I just was putzing around on the bus in this morning and said, you know what, let's try to figure out, show you exactly what we're doing. Okay? So I want to show you what's happening in SRAM also. All right? So just do a new project. We're going to run this on the 169. Obviously, we're going to do a simulation here. All right, let's build this guy, and let's go through step by step what's happening here. All right, we're going to be jumping back and forth between the I/O and the processor, okay? So get your I/O view up there first, and bring up port B. gonna be going back and forth with port B and C, and we're gonna have the processor view. And go down here and go to IRAM, and let's start off with like memory location 20, all right? Just so we can see what's happening. All right. What we're going to be doing is we're going to be looking at port B and C, so we're going to be seeing things happening right in here, 23, 24, and 25, okay, at those SRAM locations. So we're going to be, again, the point is, we're going to be reading and writing down here, right in here, all right, in SRAM, okay? All right, so now we're going to load up R16, and that's going to be a data direction register just for there, all right? And you physically see 024 has an FF in it, okay, here. This is the SRAM memory location right there. And if you go down here, 20, 21, 22, 23, 24 in SRAM has that in it. So that is exactly that. Okie dokie? All right. Is everybody okay? All right. Now we're just going to load a 5.5 in just for funsies. It could be any hex number. And I'm going to out it to port B. You now see the 5.5 here. Now you see memory location 2.5 has a 5.5 in it. And if you go to SRAM, there's your 5.5 right there. So we had just written a memory location 2.4, written a memory location 2.5. Okay? Now I'm going to load in a Z. Now what I'm going to do is I'm going to read this. This is going to sit on these pins, and now I want to read them out. I'm going to read them into a register, okay, into another register. You'll notice that as soon as you hit that, these go blue, but they're still high, but these bits follow it. Because these are the in-pin ins, all right? They follow it. So now I am going to output the data direction register for this port. I now want to read these bits in. I have to convert this data direction register now to a what? All zeros. It's got to be all zeros. But when they're all ones, they're still all ones right now, even though they're highlighted in blue. They're still ones. So this port is still an output port until we out all those zeros to that data direction register. Oops. Now you see that we've just written the data direction register is now written as all zeros. Okay? It's highlighted in red because it's changed from a blue to, from ones to zeros. And now what we're going to do is we're going to read in to R18 what was on those pins right here. We're going to read those pins in. Okay? So now if I go over and look, hit your processor, go down to R18, and you'll see here's R17 that was for the data direction register. There's R18. So we had written the 5.5 to the port, and now we've read it into R18. Everybody okay? All right. Now I'm going to make port C an output port. Okay? Now we're going to go here. If you notice that, and go to your processor, go to the I/O view, now click on port C, you will see memory location 27 has an FF in it. You will go down here and look at 20, 21, 22, 23, 24, 25, 26, 27. SRAM memory location down here has an FF in it. So we just set the data direction register for port C, which sits at that SRAM location. Okay? Now I'm going to out if you notice here, I'm going to use a different, I'm going to use the IO address for this guy. I'm going to out to 08, that one, R18, okay? So I'll just take, I've read in from port B the 5.5, all right? And then we've taken it out and we put it over at R8, at memory location 08, okay? And here it is. Here's memory location 7, 27, here's memory location 28, all right? So again, there's two ways. You can use the IO address, or you can use the, pin Bs, that stuff. Okay? And just outing port C. Now I'm going to take the contents of R18 and store it in memory location 25. Just there. Okay? All right. Now do me a quick, let me just all right, grab your clicker. All right. A is, you understood what I was talking about. B, you kind of got it. C, yeah, it went over your head. Okay? So give me an A, B, or C. All right? So I don't think I did this justified. All right? Come on. Give me the truthiness. Truthiness. All right? So we kind of got it. Okay, looks like we're halfway there. All right, let's revisit it. All right. All right, so again, what we're doing here is this sets up the data direction register for B. All we're doing is we're forcing port B to be an output. Okay? Now I'm going to write to port B. Okay, so we're going to write something to it. Okay? So now we've written to port B. So now port B, now notice that these pins, the input pins aren't high yet. They will go after this command. Okay? So that's all we did. We've written it, and then you see now these pins will follow that. Okay? The reason they follow it, why do they follow it? Does anybody have any idea? Because basically what you've done is we set the data direction register here to all ones. This could be any pin on port B. So this is a short circuit. We've written out to it a 1. Well, what's following it right here? The input pins. Okay? The input pins. All right? That's why you see it in the simulator, it's following. Okay? Because if I have 5 volts sitting out here, what's going to be sitting right here?
5 volts.
5 volts. If I have a digital 1 sitting out here, what's going to be sitting right here? A digital 1. Okay?
So it had nothing to do with that LDI command?
No, LDI is just loading it up. No. Yeah. You mean here?
Yeah, because it goes high after that LDI.
After this. All right, so now we're going to out the data direction register to be inputs, because we're going to read from it. So now the data direction register goes to all zeros. Now we're going to read these pins here. These pins here are going to go into R18. Okay? So we're going to read them in. Here they come in. Look at the, go over to the process review. There's R18, it's highlighted in red, and it's got the, we just read those pins in. Okay? Now we're outing it. The data direction register for port C, we're going to write to it. We're going to take the contents of R18, which was what we read in from pin B, and write it to port C. So now we've written it to port C. Okay? And if we go up and look at the I/O view, port C is now, okay? Out of port C. And there we go. All right. All right, so I have a whole bunch of examples in here. Let's just pull that a little bit. Now, if you notice that in your textbook, I forget what page it's on, but here he gives you the memory and the I/O addresses for the Atmel 32. You'll notice that these are all different. We had 23, 24, and 25 were port B memory addresses in SRAM. Notice that 23, 24, and 25 have stuff to do with the analog to digital converter and stuff, all right? So they're different addresses, so it's nice to just use pin B, DDR-B, and port B. Use the names, you know what I mean? Because these addresses, because as soon as you pick your processor, it'll take care of it for you, because the include file has all those EQUs in it that takes care of all these numbers for you.
On like a test, we'd be expected to know.
No. I'm not. You look it up.
Yes.
Now, if I give you a manual and say, go give me the address of where, port B is, give me the I/O address and give me the memory address, you should be able to look that up. I mean, it's just, you just go to the manual. So, like in here, let's see. Let's see where that, you just go to your AVRs, let's just pull up the 169P manual. And you just go down here and click on I/O, and then if you come down a little bit, oh, I think I passed it. Yeah, that's the count. Well, it should be down here. A lot of data in that manual. There you go. Here's all the general purpose registers for the 169P, and here's their addresses. Okay? So it gives you all that stuff there. So yeah, if I were to ask you, you'd have to have the manual. You wouldn't memorize this stuff. Okay? All right. All right, so now we're going to do some, we're going to, let's see. Oh, so now we have, there is some I/O and bit manipulation stuff that you can do. And again, oops, let's go back. You can go and set specific bits, all right? So SBI is to set a bit on an I/O port. CBI is to clear a bit on an I/O port. You can test bits. Testing bits allows me to check if a pin is high or low, and then do A or do B. All right? So I can skip a bit if it's cleared in an I/O register and a bit. I can skip a bit in the I/O register if it's set. All right? So one is clear, one is set. All right? So the SBI basically has SBI port D, pin 0. That sets pin 0 of port D. All right? It's set to 201, okay, or 3 volts. SBI DDRC, pin number 5. That sets the data direction register, pin number 5, to be high, which now that's going to be an output. All right? I can then clear the bits. For example, if I want to clear the bit on port D0, there it is. Clear the bit in the data direction register for 5. There it is. All right. So now what I'm going to do is write a program that continuously toggles port A, pin 4. You set the bit in the data direction register for pin number 4. I then set the bit on pin number 4 to go high. I then clear the bit on pin number 4 to force it to go low, and then I just jump back and forth in here. So that's all it's doing. So that, if I had an LED on there, it's just going to go on and off. All right. Here, let's see. Oh, I was going to blink all the LEDs here. This has, I do a lot of front end stuff here because basically I'm going to use a delay subroutine with a counter. And I'm just setting up my RAM here. And then all I'm going to do down here is I am going to have a temp, all right, which is basically going to be an 8-bit array of numbers, okay? We're going to have an 8-bit array of numbers. We're going to out at the port B, or we're going to complement it out at the port B, call a delay, then jump back to main. So all it's going to do is blink, blink. And you can run that. That's blinking all the LEDs. I wanted to get to another one. This down here, you'll see this delay count stuff, and this pre-scaler. This uses the timers, all right? So we're physically using the timers to set up, and this gives me a 1-second delay. When we get the timers, we will get through all this stuff because you can actually set up any kind of timing sequence that you want, okay? And this is all done in assembly language over here. Turning them on and off with a delay. Let me just move a little, because I think we did some of this the other day. Yeah, and I showed you how to do a port. Inputs and outputs. All right, yeah. This is, all right, what we're going to do is a switch is going to be connected to pin PD0. Write a program to check and perform the following. If the switch is set equal to 0, I think I actually used PD2 on the video. So this might be PD2. All right, we're going to, if the switch is 0, send the letter N, ASCII N to port B. If the switch is equal to 1, send the letter Y out to port B. Okay, so we're going to be sending ASCII characters out to a port. These ports are all 8-bit ports. I'm going to have 8 LEDs sitting on there, so we're going to actually physically see the binary equivalent of these ASCII numbers are going to be written to those ports. So here's basically what you want to do. Flow charting is essential, all right? So what I'm going to do is I'm going to make an input. I'm going to CBI, DDRD. Yes, it changed that on your slides to a 2. Because I'm going to basically clear bit on the data direction register for port D, pin number 2. So I'm going to use pin number 2 as an input pin, all right? I'm then going to load up the data direction register. I'm going to output for port B, because that's where all my LEDs are tied to. I'm going to set up the data direction register for port B. Now, here's where I do my testing. Is it a 1? All right, so we're going to check if the bit is set on pin D, pin number 2. If it is a 1, we're going to jump over and we're going to load in an ASCII Y. Send it to port B and then repeat. Go back. Just go back here. If it's a no, we're going to jump over, go down here and load in an ASCII N, send it to port B, and then simply go back and repeat. Okay? So that's all we're doing. The code for it is right here. Again, once you flow chart it, and once you get your instructions, it's just very simple to map it out into the assembly code. So here I'm going to clear the bit, load the R16 out the data direction register, do my testing, test if the switch is low, jump to over, which is down here, which is going to output an ASCII N, which is a binary, or in hex, it's a 4E, output it to the port, and then come back up here to again. If the answer is yes, it's going to skip over this, and it's going to output into register R16, the Y, which is a 5-9 in ASCII, out at the port B, and then just jump back to again. All right. And if you go to TU Portal, I think it's the last, yeah, switch down here. Takes a couple seconds to load. I don't know why that audio is so low, but all right, let me just go through this because I think it's instructive to see exactly what I'm doing. All right, here is port B is sitting over here. All right, pin 0 here is going to get attached through. Well, let's first start off with VCC and ground. Watch this wire here come all the way back. It goes to the lower part of port D, next to pin number 7. That is ground. So this whole rail here is all tied to ground. That rail there. If you go over and look at, let's see, it's right here. This guy comes back and is tied to just above the ground. That's VCC. That's 3 volts. All right, so you can attach ground and 3 volts there. This whole rail here, all this along here, is tied to 3 volts. So I have ground on one end, 3 volts on the other. All right. Then from ground, I go through a set of 270 ohm resistors into each LED, and then each LED is then tied to the port. Okay. So each one of these is tied to the port. So now what we've got here is, so here's all of these pins here are physically connected here. Over here I have, this one is switch 1, 2, 3. 1, 2, and 3 are all jumped over to pin 0, 1, and 2. So switch number 1 over here is connected to PD0. Pin number 1 here, if you follow it back, it's connected over here to switch number 2, which is, and that's PD1 here. PD2 is connected right here. So this is the one that we're going to be using. This, which is switch number 3, is connected to port D, pin number 2. So now what's going to happen is, if this is set low, all right, if it's low, or off. If these switches are off, down here, what am I going to read on port number D? If the switches are off, what's over there? The switches are off, it's open circuited, so each one, again, remember that the port is tied to VCC, which is 3 volts, resistor, switch, ground, PD2. So when the switch is open, what is that port reading? How many volts? 3 volts. These ports are active low, all right? So when that thing is high, it's reading a 0, okay? So now what is happening is, if you'll note, well, let's see, if you notice here, let me go back to the flow chart real quick. Is it a 1? No. Loading the ASCII in, all right? Somebody's phone. So if you get that, this bit over here is tied to PB7. That's the most significant bit on port B. And it goes down to the least significant bit on port B is here. All right, so that's tied to pin 0 on port B. So it goes from the most significant bit on the right to the least significant bit on the left. That's how they're tied to that port. So what you've got here is it's going to put out the ASCII yes, which is 5-9. So you'll notice that the most significant bit is low, high, low, high. So in hex, that is the number 5. And you see here, high, low, low, high, that's the number 9. So there's the 5, there's the 9, which is the ASCII Y. Okay? So now we've got the N was sent out, the ASCII no was sent out, because we just pulled, that switch was just thrown, bam, we are now active low, all right? So now we're going to have a 4E, so 0 for the most significant bit, 1, 0, 0. So this is the only LEDs on. So there's the 4 part right there. That's 4. Then you'll notice that this bit is high, this bit is high, that bit is high, and that is low. What's the ASCII, or what's the hex equivalent of that? That's E. 4E. Okay? Alright, make sense? Alright? You know you're getting a quiz Friday. Not enough time today. Huh?
Oh, what?
Chapter 2 or 3? I didn't do 4 yet. Yeah.
So not chapter 4?
Not yet. That'll be on the midterm next week.
So like branches and roots and stuff?
So it goes up to chapter 4.
Alright, so that's basically it. That's all the I/O stuff. Alright, so now you're ready to we'll be getting into some hardware in the lab next week then. Alright?
Dr. Humphrey, is chapter 5 gonna be on the exam?
Yep.
Okay.
Yep, I'm gonna start 5 right now. Unless there any questions.
So why is he doing this?
Talk to me. What do you got?
So when the data direction register report is all zeros, that means you're setting it as an input.
Output.
When
Or
you-
no, input. Input. I'm sorry. Yes.
Zeros is an output. So when you're trying to get when you're trying to get those LEDs to light up, you're writing some hex number ones and zeros to,
Well, here. Let's go look at the code.
and then when you output it, that's when it gets put onto the pins.
Hold on. All right, that's the flow chart. Here's the code for it, okay? All right. Here, now in this case, I set the bit on pin pin number 2 on pin D. I clear that. So the data direction register on port D, all right, is now going to have pin number 2 as a 0. It's going to be 0. I didn't do any of the other pins on the data direction register on port D. I'm only playing with that one pin because that's where my switch is. I could have used other switches. I could have done, you know, if 2 switches are thrown, send out a letter L or something. You know what I mean? We could have tested it any number of ways. But I'm only using one pin, so this sets up the data direction register on port D, pin number 2, to be cleared, CBI. Clear the bit on the I/O port. Then we load up. Now I'm going to set up the data direction register for port B because all my LEDs are tied to port B. I set up the data direction register to be all ones. That's an output port now. So this is forcing pin 2 of port D to be an input. That's forcing all the pin Bs to be outputs. We then check and see what's happening on pin D number 2. We're seeing if it's set. Okay? If this is true, if this guy's true, what happens? You're going to skip this. It skips it. All right? If not, it's going to go into jump to over down here, which is going to be low. All right? So here we're just testing here. And all you have to do here is just look. Depending upon what you're doing with this test right here, all right, this test is going to skip over this if the condition is true. Okay? Skips over. So, and if not, then we go into load up R16 with a Y, and then just output it, and then just jump back to again. So we're just jumping back to again here. Right up here. Here's again. All right? That's the label. So that's all we're doing. And if not, then we just send out a letter N. It's just straightforward. Everybody okay? All right. All right. Any questions on I/O stuff? All right. I had another. So hopefully you see in hardware how that's all set up. So again, in hardware, make sure that you put in these resistors in there because you don't want to burn out your I/O ports. All right, the same thing over here on the switches. I put in some, I think 470 ohm or 270 ohm resistors are sitting over there. It's good to limit the current on it, all right? he's got a whole, if you look in Appendix C, he's got a whole bunch of do's and don'ts with I/O ports out there. Okay, so there's a whole bunch of them there that basically what you want to be careful about doing when you're hooking up different stuff to those I/O ports. And what's the easiest way to burn out a butterfly board? Short your I/O ports together. Just like on the Adreno, it's the kiss of death. Okay. All right. So now we get to chapter 5, and then we're ready. After chapter 5, we're ready to do some C programming. We're going to migrate away from. Well, we'll do some assembly still. All right, chapter 5. All right, this is math and logic stuff, all right? Here's where we'll get into some signed and unsigned arithmetic. All right, we're going to look at the objectives, look at 2's complements you basically use this for a subtraction, carries and overflows, logical instructions and masking, doing some compares and branching, shift, rotates, and data serialization. All right. Unsigned numbers. Unsigned numbers. This is just an 8-bit unsigned number. The most significant bit is D7. Down to the least significant bit is D0. 16-bit unsigned, D0 up to D15. Okay? The range here for 8-bit unsigned numbers goes from 0 to 255. All right? For 16 bits, you go up to 65,535. All right? When you got signed numbers, obviously the most significant bit is the signed bit. So now no longer is this used to get the magnitude of this number. All right? So in this case, you can go from minus 128 to plus 127. If this is a 0 and all these are 1s, that's 127. If this is a 1 and all these are 0s, that's minus 128. Okay? Same thing on a 16-bit. You can go from 32,767 to minus 32,768. Okay? ASCII equivalent. The ASCII table just is basically what it is. It gives you all the ASCII equivalents for each bit. So if I had, like here, we had the letter Y. The letter Y, you go over, and that's 1001, which is the 9. Right? And I go over to here, and 101 was the 5. Right? So when we sent out a 5, the most significant bit was 101, followed by 1001. Okay? So that's how you use the ASCII table. All right? We did some adds with basically using registers, and we'll see how the flags are going to get affected. If I have an F5 with an OB, I'm going to add those two together. And you'll notice here that when I add these together, the F5 in hex gives me the F. There's the 5. The OB in hex gives me the zeros with the B. When I add them together, it's going to be all zeros here. And the carry flag will be set. Because I had a 1 coming out of the most significant bit. So R20, R21, which is right here, is going to contain all zeros, and the flags are all going to all be as follows. C equals 1, Z is equal to 1 because it's a 0 result, and H is equal to 1 because there was a carry coming from D3 into D4 here. Okay? So we had a carry here, that set the H flag. We got a 0 flag set because the result in R21 is all zeros. And then we had a carry because we had a carry. Carry me over. All right. All right. Have a good one. I'll see you on Friday.